Welcome to this series of films about logic control. In this first film, I will explain what a PLC system is. Then, in the next film, I will introduce the programming environment, codices. And the following films will continue on how to program a PLC in different languages. But we will start with what the PLC system is. PLC is short for Programmable Logic Controller. When they were first introduced in the 1970s, the systems were simply called Programmable Controller, but the short form PC is now known as Personal Computer, and the L in logic was inserted in this name to avoid confusion. In the 1970s, when PLCs were introduced, our industry was automated by use of relay systems. So the PLC system came to replace those systems of relays. The PLC system is programmed by a computer, and the program is then transferred to the PLC system and run there. There are many developers of PLC systems, just to mention a few: ABB, Siemens, Mitsubishi. In these films, I will use a Crevis system. That system is programmed in a programming environment called codices. I've chosen to use codices because it's free to use. You can download it to your own computer if you have a Windows computer, and thereby you can try out the examples yourself. In the start of PLC programming, all manufacturers were trying to be fast and developed their own set of programming tools and systems to build programs. But soon enough, a standard was developed, and the standard that is now existing is IEC 61131-3. And I will stick to this standard, even though there are special features in codices as well. But I stick to the standard, which means that the knowledge from these films can be transferred to other systems as well, even if the programming environment in itself will be a bit different. I will start with some basic terminology to control systems to define different kinds of signals. This is the control system, for example, a PLC system, and this is what we want to control, the process. We will send signals from the control system to the process. In order to control it, we will control it through the actuators. The actuators are what make things work in the process. For example, a motor to a pump. We'll get responses from the process. The process will tell the control system what is going on here. And to know what is going on, we need sensors. Sensors see what will happen in the process and send back information to the control system. Now, I am defining input and output signals from the control system's point of view. A signal from the control system is an output from the control system. Even though it's an input to the process, we will now define it as an output. Similarly, an input to the control system is now defined as an input, even though it's an output from the process. So we use the control system as the reference point. The output is a signal from the control system, and the input is a signal to the control system. The reason for that is that we have input and output modules in the control system. We can have digital outputs, analog outputs, digital inputs, and analog inputs. The control system in itself cannot use analog signals, which means that we need to have some kind of digital to analog conversion or analog to digital conversion here. This is a photo of the Crevis system that I have in my lab. I will be using it as an example of a modular PLC system. We can see that it's modular here. Each module can be removed, put in another place, and they are all connected here. Many PLC systems are modular, which means that they are very flexible. If we want to have more input modules, we can just put one extra in. In this system, we have the CPU here, where the program is run. Here we have two Ethernet cables, and they are used for communication with the PC that's used for programming. It can also be used for monitoring. And we can also have an Ethernet cable for connection to other control systems. We also have a hardware stop and reset on the physical PLC system here. Now to the modules. The first modules I have here are input modules, digital input modules, which means that in all these cables I can have digital signals into the PLC system. We can see that we have 0 to 7, 8 signals per module, and I have 2 modules here. Remember, it's only an example. I can put in more or less modules if I want. Here I have my digital output modules. They are also connected to 8 signals, 0 to 7. They look twice as big, but that's because they need a reference signal as well. I have 2 output modules, 8 signals in each, which means that I can send out signals to 16 different actuators or lamps or something else that I would like to control. Here I have an analog input module where I can receive analog signals in the range of 0 to 10 volts. In this system, this range can be changed by changing this module. And I also have an analog output module where I can send out analog signals in the range of 0 to 10 volts in my system. I can change this module to other ranges as well. In my example PLC system, I have 16 digital input ports, 16 digital output ports, 4 analog input ports, and 2 analog output ports. They can be connected to the process to be controlled. We will also need to connect it into the PLC, which means that they have to be addressed. The addresses in the crevice system are like this. We have a percentage sign, IX 0.0. That is the first input port. And the 8th input port in the first module is percentage IX 0.7. And then we have the next import module. And that is addressed in the same way, but with 1 here. So 0 for the first one, 1 for the second, and so on. Similarly for the digital outputs, but now we are using a Q here instead. Both the digital input signals and the digital output signals are just true or false, on or off, 0 or 24 volts, which means that we will receive a Boolean. The analog signals need to measure the entire range from 0 to 10 volts, which means that we cannot have a Boolean. In those systems, we are receiving a word or sending out a word, which is 2 bytes, 16 bits. And here again, we have I for input, Q for output. Here they are numbered 1 to 4 and 1 to 2. And remember, inputs are coming into the PLC and outputs are coming out from the PLC. These were the addresses in my example PLC. Generally, the addresses are defined like this. We have the percentage sign, it's always there, and then we have some kind of memory prefix. That can be I for input, Q for output, and M for memory, internal memory. And then we have the size of the signal. We've already seen X for bit, on and off, and W for word, 16 bits. You can also have B, byte, 8 bits, double word, 32 bits, or long word, 64 bits. And then we have the numbering at the end, which I said 0.0 is for the first input port in the first input module. How those numbered are defined is not in the standard, which means that different manufacturers have their own system for those. The example I had is for the crevice system. Programming a PLC system differs a bit from programming, for example, a microcontroller. The execution in a PLC is cyclic. It's using an infinite loop. It's always running, well, until we stop it, from top to bottom, top to bottom, top to bottom. We always start by reading data from the input ports, Then we execute all the programs in the specific order, and then after that, the PLC system writes to the outputs. Which means, for example, that if I have connected one of my outputs to a lamp, and here in my code I say the lamp should be on, and then later on in the code I said the lamp should be off. When we come to here, the output module will read the state of the lamp that we have when we come here, which is off, because I tried to turn the lamp on and I turned the lamp off, which means that I will write off. If I had written this code in, for example, a microcontroller, I could have turned the lamp on and then off in the same code because it continuously writes to the outputs. But the PLC system will not write to the outputs until the entire program is executed. Then we write, and the loop goes back to read the input data. We will not read any new input data while we're executing the program. When it's done, we write to the outputs. Now when I'm explaining it, it sounds very slow, but well, it will be in the range of 1 to 50 milliseconds, depending on the settings in the PLC. The first word of advice: do not write to the same physical output, the output signal from the PLC system, more than once in the code, because the system will only use the last value written to the output. This concludes the first film. In the next film, I will introduce how to program a PLC in general and in the programming language Codesys.